Let's talk about Lewis structures. Not you, go away, Lewis. We're going to talk about Lewis structures for molecules and how we're going to draw Lewis structures. We have a set of rules here that we are going to follow as we're drawing the Lewis structures. And if you follow these rules, you will end up with the correct Lewis structure. There is a little bit of stuff here at the beginning where if it can sometimes be unclear how you should arrange the atoms in the molecule. I'm going to do my best to show you the correct ways to do that, and if it's something where it is very unclear, I will just tell you how to arrange the atoms in the molecule. So let's go ahead and look at our rules. Rule number 1. Arrange the skeletal structure of the molecule. This is essentially saying what is connected to what. How are the atoms actually connected together? Not in terms of how many bonds or anything like that, just what atom is bonded to this atom, and so on. So the atoms with more unpaired electrons are usually central, which is a way of saying stuff further to the left on the periodic table is going to be central, because all the stuff we're going to be doing here is the nonmetals. So as you go to the left on the table, the nonmetals will they'll have more unpaired electrons. So carbon has, and everything in the row with carbon has the most. Carbon has 4 valence electrons, and so all of its electrons are unpaired. And then as you go to the right from carbon, you go to nitrogen, oxygen, fluorine, and you get another electron with each of those, and so they start to pair up from that point. So the thing with the most unpaired electrons is usually in the middle of the molecule. Things with fewer unpaired electrons are usually terminal, which means they're at the end of the molecule. We're not going to do anything too crazy in terms of Lewis structures. We'll have a few molecules where it's not just a central atom and then things attached to it, but I would say 75% or so of the Lewis structures we're going to do, we have some atom in the middle, and then we have stuff attached to it, but that's as far as it goes. There's just a central atom and then things attached to it. That'll be most of the Lewis structures that we do. All right, and hydrogen is always terminal. You're never going to have something like this, where you have a carbon attached to a hydrogen, and then there's another hydrogen attached to that hydrogen. Hydrogen only wants one bond, and that's all it will ever have. You will never, ever have hydrogen with a lone pair bonded to something else. I mean, you never have hydrogen just with a lone pair all on its own. Like, even that you're never going to see. Hydrogen will only ever be just a single atom attached to something else with a single bond. It'll never be a double bond, never be a triple bond. It will never have lone pairs. Hydrogen is just single bonded to some other atom. That is the only thing you will ever see with hydrogen. So after we have the skeletal structure, rule number 2 tells us to calculate the total number of valence electrons. And we're going to account for the ionic charge if we have one. So we're going to do that using our handy periodic table. If you remember, I don't think I have a periodic table here on these slides, but if you remember, we were using the periodic table as our guide to work out how many valence electrons something has. So everything in the carbon column has 4, everything in the nitrogen column has 5, everything in the oxygen column has 6, everything in the fluorine column has 7, and it follows the 1A, 2A numbering system, or if you're using the newer numbering system, it's the second number. So carbon is in column 14, and it has 4, nitrogen is in column 15, it has 5, so on and so forth. So we're just going to add them all up. If we have a negative charge, then we would add electrons. If we have positive charge, we would subtract electrons. And we'll see examples of that in just a minute. Rule number 3. We're going to distribute the valence electrons until we run out. We're going to do that by putting the bonds in first, and usually I put those single bonds in at the very beginning. I don't wait until this point to put the single bonds in. If we know the skeletal structure up here, they have to at least have a single bond between all the atoms in the molecule. So we might as well put the single bonds in up here. So then from that point, we put lone pairs on terminal atoms, remembering that hydrogen does not want lone pairs. So all the other terminal atoms get lone pairs up to the point that they have their octet. And then if we still have electrons left, we will put lone pairs on the central atom. If at that point we still have stuff that does not have an octet, we will try moving lone pairs around by putting them into bonds instead of being lone pairs to see if that will fix our issue of having things without an octet. So let's look at some examples here. I'm going to do one or two of these with you right off the bat here, and then I'm going to ask you to try and work out the rest before we do the rest of them. So let's see, normally if this was in class I would do these on the board, and I don't have a lot of space to work with here. So I think what I'll do is I have enough space where I can do a couple here, and then when I ask you to pause the video, I'm going to actually move to a different place to write out the rest of these. So let's go ahead and do, maybe we'll do this column here. So we'll do these three, and then you can work on these six. Or actually, no, let's not do that. Let's do this one, and this one. That's a better representation. So we'll do these three together now, and then you can work on the rest. Okay, so CH2Cl2. If we're following the rules, it tells us that the central atom is probably going to have the most unpaired electrons, and that is going to be carbon. And that is indeed the case. Carbon is central in this molecule. It will always be central if you have carbon because it has the most unpaired electrons. So we're going to have carbon attached to 2 hydrogens and 2 chlorines. And I know I'm going to run out of room here, but we'll do our best. So this is our skeletal structure. Again, we're just going to go ahead and put in the single bonds because we know it has to at least have a single bond to everything. Now, we are going to add up the valence electrons. So carbon has 4. It is in the column 14 or column 4A. So it has 4 valence electrons. Hydrogen has 1, but we have 2 of them. So right now we have 4 plus 2. We also have 2 chlorines, and chlorine is in column 17, which means it's going to have 7 valence electrons. So if we add all of these together, we have 14 from the chlorines plus 6 from the other atoms. That gives us 20 electrons total to put into our Lewis structure. So the next step, we're going to start putting in lone pairs on the terminal atoms first. So we're not going to put lone pairs on carbon yet, and we'll just put those in until we run out. So we'll just pick a chlorine, doesn't matter which one. We already have 8 electrons in the single bonds that we put in there. So we're going to start from there. So we have 8, 10, 12, 14, 16, 18, 20. And I didn't stop there because I finished filling up the chlorines. I stopped there because I ran out of electrons. I only had 20 electrons to give, and I put in 20 electrons. So now I'm going to check and see if everything that wants an octet has an octet. And if I look, yes indeed, everything that wants an octet has an octet, and hydrogen, which just wants the single bond, the duet, also has what it wants. And so it is happy. So that is the correct Lewis structure for what we call dichloromethane. Let's do this one next. Into H2. This is a little bit different. The reason why I wanted to do this one is because it's not clear what the central atom is, because both of the nitrogens have equal claim to be central. And so what we're going to do is we're actually just going to put them both central. So we have both of the nitrogens together at the center of the molecule, and we're going to, a general good rule of thumb is make the molecule as symmetric as possible. So we don't want to put one hydrogen here and then the other hydrogen also on the same nitrogen. We are going to make it as symmetric as possible. And so we're going to put the other hydrogen on the opposite side. It's not always going to be the case in reality, but for our purposes, it will always be the case, just because we're keeping it fairly simple here. So make the molecules as symmetric as possible, and you're doing the right thing. All right, so this is our skeletal structure. If we add up our total valence electrons, nitrogen is in column 15. So it's going to have 5 valence electrons, and we have 2 of them. So we're going to get 5 from both, so that gives us 10. And we also have 2 hydrogens, which you've already said only have 1 valence electron. So that is going to give us 12 electrons total. So we already have 6 here in the single bonds. Our terminal atoms don't want any more. So our terminal atoms do not want any more electrons. So we can put the rest of the electrons on the central atoms. So starting at 6, 8, 10, 12. We ran out of electrons. So if we start looking at what we have so far, does everything that wants an octet have an octet? No. This nitrogen does not. This one does. This one has 8, but this one does not. And so if we ran out of electrons, not everything has an octet. We need to think about moving a lone pair to make a bond so that we can get everything an octet. So if, for example, we take these 2 electrons and we move them, we move them down here so that we have a double bond here. Now, does everything that wants an octet have an octet? Yes. Everything that wants an octet has one. This nitrogen did not really mind taking what was a lone pair and sharing it with the other nitrogen, because it still gets to claim it. It still has its full octet. Sharing it does not mean that it no longer gets to have a full octet. So they are both perfectly fine in this case. All right, let's look at our last example here. So just trying to find where the edge of my screen is so I don't... Okay, it's right there. Can't draw past that. Okay, so we have ClO2 minus. This is a situation where I would tell you beforehand what the central atom is, because it does not follow the rules or the guidelines in the rules. If you're following the rules, the oxygen should be central, because the oxygen has 2 unpaired electrons, but the chlorine only has 1. But this is going to break that rule. It's going to break those guidelines. The chlorine is going to be central. Actually, I'm just going to write it this way instead of that way. So we have Cl with 2 oxygens bonded to it. Right? Now we need to add up our total valence electrons. So we have 7 from the chlorine because it's in column 17. And then we have 2 oxygens. Both of them are going to have 6 valence electrons, which is going to give us 19, but it's negatively charged. So we're actually having, we're going to have 20 electrons, because we're going to add 1 extra because of this negative charge. The ion has an extra electron, and so our Lewis structure is going to have an extra electron. All right, so we have 20 electrons to give. We only have 4 in the structure so far with those single bonds. So we're just going to pick a terminal atom, either one, and start putting in lone pairs. So we already have 2, 4, 6, 8, 10, 12, 14, 16. We filled up the oxygens. They have their octets. They don't want any more. And so the last 4, we're going to go on the chlorine. So that was 16 with the oxygens, 18, 20. And we have a molecule, or an ion in this case, where everything that wants an octet has one. All right, hope those examples are clear. I would like you to pause the video right now and try to work out the rest of these examples. The only thing that I need to make clear to you beforehand is that the bromine is going to be central in this one. All the rest of them should follow the rules that we've discussed so far, but the bromine will be central for this bromate ion. So go ahead and pause the video now and try to work those out yourself, and then we will discuss it. All right, I truly hope that you stopped the video there and are back with me now with your hopefully correct Lewis structures drawn out. What I did was I just went in and added in a few extra slides and copied and pasted the molecules in there. So we're just going to work through these together real quick. This is going to be a little bit of a long video, but that's okay. Examples are always good. So we starting here with C2H4, just like with the N2H2, both of the carbons have equal right to be central, so we're just going to stick them both in the middle, and then we're going to make it as symmetric as possible, which would not be to put 3 hydrogens on one side and 1 on the other, but instead to have it laid out like this, with 2 hydrogens on both sides. By the way, it's perfectly fine to put 2 hydrogens down and the 2 out to the sides. It's just, I think it looks better this way. If we add up the valence electrons, we have 2 carbons. Each of those have 4. We have 4 hydrogens. Each of those have 1. And so we end up with 12 electrons total. There's no charge on this one. We already have 2, 4, 6, 8, 10 in the structure, so we only have 2 more to give. The hydrogens don't want them, so we'll just pick a carbon, put it on those. Does everything that wants an octet have one? No. The carbon here does, but this one does not. So what we're going to do is we are going to take that lone pair and we are going to move it into a double bond. So we're going to create a bond between the 2 carbons instead of just being a lone pair on one of them. And now they both get to claim that pair of electrons in the bond, and so now they are happy. We have a happy little molecule. I'm the Bob Ross of chemistry, I guess. I'm making happy little molecules here. Let's make him a happy little friend. Carbon monoxide, not really a friend of ours, but it'd be a happy little friend for C2H4, which I believe is acetylene. No, acetylene is C2H2. I forget what C2H4 is. Anyway, carbon monoxide. Only one way that skeletal structure is going to work. Like there's no other possible way to arrange 2 things. If we add up the valence electrons, 4 from the carbon, 6 from the oxygen, gives us 10. As far as which one to put the lone pairs on, you generally want to put the lone pairs on the thing that is more electronegative first. So the oxygen wants the electrons more than the carbon does, and so we'll go ahead and give it the lone pairs first. So we have 2, 4, 6, 8, 10. Now obviously not everything is happy there. That carbon is exceedingly angry with us. And so what we need to do is move 2 lone pairs in to make a triple bond. Oops, that's not the one I wanted. Eraser, there we go. And that is carbon monoxide. The thing that is really, really bad to get into your lungs. Very bad. Alright, moving on. Carbon dioxide, not nearly as bad to get in your lungs. Actually, it's not bad at all to get in your lungs. In fact, your lungs make it. Well, your body makes it, and then your lungs excrete it. Carbon is going to be the central atom. It has the most unpaired electrons out of the two elements. Oxygen only has 2, carbon has 4. So we're going to make it as symmetric as possible here. Carbon in the middle, 2 oxygens on the side. If we add up the valence electrons, we have 4 from the carbon, 6 from each of the oxygens, gives us 16 electrons total. We already have 4 in the single bonds. We're just going to pick an oxygen and start putting in those lone pairs. So 6, 8, 10, 12, 14, 16. We've run out of electrons, but our carbon is still angry with us. And so to fix this, what we will do is we are going to take a lone pair from each oxygen, give that carbon double bonds on both sides. If when you were working this you came up with a different structure that followed the octet rule, that's perfectly fine. There is one other structure that works, which we'll talk about later, but for now we'll go ahead and stick with this one. Bromate. I told you before I asked you to pause the video that bromine was the central atom. That would be something that I would have to tell you because it does break the rule. So with bromine in the middle, we have 3 oxygens bonded to it. We're counting up our electrons, or valence electrons, not just electrons, but valence electrons. Bromine has 7. We have 3 oxygens, each of them have 6, and we'll go ahead and add in the 1 from the charge as well. So this would be, let's see, 3 times 6 is 18, plus another 8 would give us 26, right? Yeah. Doing the simple math correctly in my head. 26 electrons to put into our structure. We already have 6 here in the single bonds, so we'll just pick an oxygen and start putting in lone pairs. 8, 10, 12, 14, 16, 18, 20, 22, 24, and then 26. And if you check, everything there that wants an octet has an octet. So that is an acceptable Lewis structure. As we'll see later, this actually isn't the best Lewis structure, believe it or not, but it is an acceptable one. So then the last ones here for this video, ammonia and ammonium. In both cases, it's pretty obvious what the central atom is, since hydrogen is incapable of being the central atom in anything except for this. That's the only thing where hydrogen can be central. So the nitrogen is definitely going to be central. If we add up our valence electrons, fluorine has 5. We have 3 hydrogens, 1 electron each. That gives us 8. If we count up the electrons in the bonds, we have 2, 4, and 6. That gives us 2 more to put in somewhere. None of the hydrogens want them, so the nitrogen gets a lone pair, and that makes it happy. Ammonium is going to be similar. Put those hydrogens in. They have to be bonded to the nitrogen because they can't be bonded to each other. If we add up the valence electrons here, we have 5 from the nitrogen. We have 4 hydrogens, 1 electron from each, which gives us 9, but we have a positive charge, which means that we've lost an electron, which means we only have 8 electrons in our structure. And if you look, those are already in there. We already have all 8 of the electrons in the structure in the single bonds to that nitrogen. And so this is already an acceptable Lewis structure. No need for lone pairs. All right, that is it for those examples. In the next video, we're going to talk about formal charges. These are going to help us determine for those molecules where there is more than one acceptable structure. Because if you remember back here, I mentioned that you might have arrived at a different structure for this that was also acceptable. And I also mentioned that there was an even better structure than this. So both of these things are acceptable, but there are alternate structures that are also acceptable. And formal charges are going to help us determine which one is better. What is the best structure? So we'll talk about that next time.